Okay, chapter one will be on a bit of an overview to put everything on the right perspective. There's some definitions that we want to share next, so that all of us are on the same page. Then there are a few, well, I would say technical terms that I will also share, so that you know exactly what I'm talking about. Because remember, the motions we are going to, in spacecraft dynamics control, we are going to deal with motions of the rigid body. So there is a lot of difference between what you have been exposed to in space before and in this particular subject now. So let's go with I'll start discussing on system context. Now, translation and rotational motion. Remember, translation motion you have been exposed to. That is orbital motion. It's already done. You have been trained to understand what is translation motion from one point to another point. You can now understand how to insert a particular rigid body from planet Earth to the particular orbit. Now, this particular subject, spacecraft dynamics control, is going to teach you from that particular point how am I going to operate or fly this particular rigid body. And remember, your task is basically planet Earth. You know you can do Hohmann transfer, and you know you can put in basically the exact orbit. Then you ensure that the calculation of delta V is good enough basically for you to orientate the planet Earth. So this is what you have calculated already. Good. Now, this is done. The calculation is done, so it can do this for you. But it is still in the orbit. Okay? In order for it to be very stable and to maybe point or look at planet Earth, spacecraft dynamics control. So this motion is all rotational motion. You can stay in the same orbit. You will be insensitive towards orbital mechanics. You will be insensitive. Because orbital mechanics is going to treat you as a point mass. It's a point. It's a point mass. Spacecraft dynamics control is going to treat you as a rigid body. So when you have your rigid body, then you have inertia. So then when you have inertia, in a point mass, this is the whole lump, it's just a mass. So no matter, you can just imagine it's a sphere. No matter how it is going to turn, as long as it's in orbit, space mechanics see it is perfect. That's it. Suppose space mechanics job you have done. You have done this. Now it's not good enough. You need to make sure it is stable. Then I need to treat this as a body. So throughout this derivation, you will hear words like inertia, because it is a rigid body. So when we are talking about rigid body, we need to know what is the inertia. Now it is a mass, but we don't need the inertia. When we have the inertia, then we can do the kinematics method. We can do the kinematics method. Yeah? Okay. So therefore, if I say system, I refer to spacecraft satellite. So system means when I say spacecraft dynamics control system, so you know the satellite system. So please, that is the term. Now the view. So this whole system is going to remember the control system. When I say this control system, so it's a control system, the satellite control system. So when I have control system, I should have defined the controller, the plant, the measurement, and basically the input. Okay? So let's see the motion of the satellite. Translation motion is basically 3 degrees of freedom. You have position and velocity. Okay? You can have either position or velocity. That means what? 3 degrees of freedom, right? You have R1, R2, R3. Position. Velocity X, velocity Y, velocity Z. Done. That is translation motion. That's all what you have learned in space mechanics. Okay. Now extend to rotational motion, also 3 degrees of freedom, attitude and angular rate. Okay. Also have to two quantities. Attitude is just like the aircraft. This all rotation. Okay, so 1 point. This is it. This is translation. Okay. Okay. Then you have angular rate. When you have a rotation, then you are going to have, if it's a constant, then you will have an angular rate. This one. This is also an attitude motion because you are not moving anywhere. You are on the same spot, then just you have attitude. Then you have also the rate. How this happens? When you have the attitude, attitude is an angle. Derivative of attitude will give you rate of angle. Right? Radian per second. Radian, rate will be radian per second. What do you mean by radian per second? So radian per second is actually this velocity. This one. So it's already have this motion. Along this axis. So if you have three axes, this guy is, this axis is also, and this is also. But remember, when this rotates, what happens? This one will go up. When this rotates, what happens? This two is going to go up. When this rotates, this one is going to go up. Okay? It's very, very important. It doesn't mean that this rotates and this. If you look at him, he's not going to affect himself. He's just rotating. But he is going to tip the other two axes because we have three axes. So if there is a rate, then it's even worse because there's a rate. Keep on doing it, can be the other way. Rate. But if it's just an attitude, there is, okay, rate is 0, but attitude is 1 degree. But there's no rate, 0. From time 0 to 1, there will be a rate. Rate of changes from 0 to 1 degree. That's rate. But after time 1, let's say there is no rate, it's 0, it stops there. So your axis, instead of like this, it will be like that, stop. Now what you have to do now? You have to correct it. Why do you have to correct? Assume this is a axis. Normally this is a nadir. Nadir pointing your yaw. Okay? Better like this. This is your yaw. This is your flight direction. We will define that later again clearly, but for today, planet Earth, yaw, roll, pitch. Okay? You are flying this way. Every time your yaw is looking at the planet Earth. Now, what happens if this rotates? Where are you looking? Okay, this one. This towards to planet Earth we call nadir. Nadir pointing. Nadir is towards to center of planet Earth. Assume I'm going to do this 180 degrees. It is going to be what? Zenith. From center to sky, out. Zenith pointing. If you look at zenith pointing, are you looking at planet Earth? No, you are not. You have to come back. So this correction must be done. This is what is important. Okay? So we will define that. We will write equation. We will understand the equation. We do a bit of derivation because this is of course in maybe the basic subjects you don't have to derive. You can end up using, but this is actually an elective subject. Good to know what is the derivation. So we will do that. Then let's see how it's going to develop. Again, temperature of satellite is, of course, is important in the system. Reason being, performance of all those actuators, especially sensors, the measurement, very sensitive to this. So, if you learn satellite technology, thermal control system is extremely important. Even as you know that a maximum temperature of 50-60 degrees is a lot already for satellite. It is not too little, it's a lot already because of this sensors. Sensors is very, very sensitive. Yeah. Okay, translation motion is orbital motion. All this you should have learned in space mechanics. So you look at the actual difference. Translation motion takes position and velocity of the spacecraft center. Now orbit changes are possible only with the tuck downs. So observe the constraints due to Newton's law we know, Kepler's law we have introduced. Newton's law has told us basically how to establish the gravitational relation between two bodies. Okay? Kepler's law have told us how can we stay in planet Earth orbit. We got three rules, remember? Okay? So that is done. Huh? So another important thing is also Newton has helped Kepler literally to solve his equation. Without Newton's finding, we can't solve Kepler's equation. So both these are very, very close to we are using. Okay, good. Then you have open loop control from the ground, very slow dynamic. This is basically, remember your station keeping. Towards the end of orbital mechanics, you would have done the exercise of station keeping. How to station keep, how to do a north correction, south correction, east, west corrections that you would have gone through. So this is the open loop from the ground. That means you tell what to do. Why it is like that? Huh? Why we have to do that? The difference is this. Attitude control is 24/7. When you on the satellite, it's already doing attitude control. There is no time it is stopping. There is no switch off. It's already doing attitude control. It's sensing always. Are you in the right path? It's sensing always. Sensing. But orbit control, it is not 24/7. Even in orbital mechanics, you have learned once in a year. For example, inclination correction. Not often. We don't do that often because we can't afford it. In fact, the nature of those disturbances also disturbing not severely every day. The cumulative for a year, yes. Then we do one correction a year. It's fine, or two corrections maximum. And it is going to be very costly because a lot of fuel need to be used. And we know for the fact that the last thing that we want to do in space mechanics, which is the orbit correction, is inclination change. Right? Inclination change is very, very costly. So that means what? So much of fuel you are going to use. So you don't do often. Or even altitude change, you don't do often because too much of fuel. But at attitude business is 24/7. Can I tell you that it is not even 24/7, it is every second. The system is on. It is just like this. When you on the light, that is a control system. Okay? That is a control system. So there's nothing else. So it has to be that one because you have to keep on sensing where you are. Attitude control system, please do understand that a good overview for you is this. Orbit control system, and it's very different compared to attitude control system. Assume that your eyes, when you want to walk, you need to open your eyes every time. So when I want to fly, I need to open my eyes. Otherwise, I do not know whether I am just doing this and flying. But as far as orbit control is fine, there's nothing wrong. But attitude control has a lot of problems. So I need to open my eyes. So I need to open, if you walk, you open your eyes every time, right? So EAS or attitude control system is like that. That's the difference. Important, rotational motion. Now, we come to attitude motion. Let us define and understand this very, very well. Okay. Now, Rotational motion is rotational state. It's basically its attitude state and angular rate. I told you two components is important. The orbital mechanics, two components. Here also two components. Frame is actually with respect, you see body frame. It's a body fixed frame. I will explain afterwards. Body fixed frame with respect to the reference coordinate frame. Okay. So just like your space mechanics, you have geocentric coordinate system. That means from planet Earth, then you have one coordinate system. It can be, let's say, in the altitude. So you have a x, y, z. So you must have at least two coordinate systems basically to define where you are, correct? Otherwise you can't. So you must have one reference and you must have one current. Likewise, you need also same thing here. Okay. Onboard autonomy, which is a closed loop operation. So when you talk about closed loop operation, you don't interfere. It is an intelligent system. Because why you can do closed loop? Because you do sensing 24/7. Every second you do sensing. It's supposed to be an autonomous system. But if you do a ground command, that is not a closed system. That is basically you decide. So ground station comes in there. Ground operator, ground system operator, they will decide when they want to do the correction. It's all decision that you make. Okay? So that is the reason inclination change. It is not automized. You decide as an operator from ground station, altitude change, eccentricity change. All these changes in, you want to change your orbital element. Except for that, you don't change your, what is that, you change the inclination for sure, but you just don't change all at one go because you can't just split for it. Yeah? So that is extremely important. Alright. Now, mission parameters basically, why it is so important? Because the payload must always look at maybe planet Earth. Let's say you have a camera. You want the camera to always look at the planet Earth. So can you do this? Okay, every second there is one man is looking out there. Whether this camera is correctly aligned to me or not. Then no. Then after you need to go back right. Then another man comes in. It's like running a relay. So we can't afford to do this. So that is the reason we need to optimize that. So it is basically all that is done. Okay, now attitude slew maneuvers, just please mark this. Slew maneuvers is sometimes come from ground. We decide we want to do slew maneuvers. Okay? And likewise safe mode, etc. we decide. The rest is basically autonomous. So technically you can sleep this movie with the attitude control system on board or attitude and orbit control system on board. You can sleep peacefully. You just have to, the telemetry will tell you whether the system is healthy or not. Okay, now this is important. I need to define two coordinate systems in order for me to move on with this subject throughout this semester. So let me clearly define to you. Center is center of matter, geocentric, right? Now, from here, let's say I define another coordinate system here. I just simply call it x, y, z. This is good enough for me to define to do orbital mechanics because this will be fixed. Geocentric is fixed. Here is fixed. Okay. So here fixed, here moving, right? Correct? Done. When this thing happens, I can sense this, right? I can use GPS basically to correct this. We will do orbit control towards the end. So this coordinate center, geocentric coordinate and XYZ coordinate here is going to take care of this system. Which system? The orbit system. For additive system, I don't need geocentric. What I need to have the body coordinate. I need to know what is this. Okay, we must have a coordinate here. I have this coordinate and I must have a coordinate which is fixed here, which rotates throughout. Okay? Now, and this particular coordinate in attitude control system, we call it local vertical, local horizontal. The difference now, remember this. Remember that I told you there was another coordinate here, x, y, z, which is important to establish your position with respect to geocentric coordinate system in orbital mechanics. It is still important. The difference between that coordinate here is that has a z up, yeah, up. The y is basically is up. Same. X, you can have x, you can have R1, say 1, 2, and 3. That is practically is related to the orbital mechanics coordinate system. Okay. Now the difference is here is when you have defined local vertical, local horizontal is practically is this one. Now this local vertical, local horizontal is fixed. It doesn't move with respect to the body. Okay? What moves with respect to the body is the body coordinate x, y, z. Okay? So please understand. Two coordinates is involved here. Local vertical, local horizontal. So this is, I can define you now here. This is your pitch roll. Roll is flight direction. This, so please do fix this. This is for attitude control. Fix this always. And yaw will be always facing here. And roll will be always tangent. If it's a circular orbit, it will be tangent. Tangent to the orbit. That is done. So local vertical, local horizontal is done. So what you have to see now, you look at the body coordinate now. The body coordinate. Now, why I say, you see, let's say the body coordinate is x, y, z. Let's say this is the body coordinate, x, y, z. It's in the middle, right? Let's say I establish x, y, z. If the x, y, z for space mechanics, if this rotates, it doesn't really matter because it is still a center, so it is insensitive. So the same coordinate system, I can use it basically as my body coordinate actually. That's how it is. Same, I use the body coordinate. My body coordinate is actually the coordinate which is fixed to the body. So happen that we don't have the variation, or rather we don't talk about the variation because in space mechanics we do point mass. So we don't talk about any variation in terms of the inertia. So but here yes. So this body, how this body is with respect to my local vertical, local horizontal, it's the definition of attitude. Period. Done. Nothing else. That is attitude. So I must make sure if I want a perfect mission, I must always have my Y body must be always here. My Z body is always here. My X body is always here. But exception to it, my Y body is basically, if you really will do the derivation, is actually is projection of this. It is supposed to be here on this. The vector is here on that direction. So it's a projection. So it's going to be negative to this here. Because remember, right hand rules. So when you have even let's say you have a top, so it will be basically in an up direction. So towards the down, so practically it's a projection. But don't worry about this derivation. We will derive this again nicely so that you can have that actual equation finally. But please understand the concept. Attitude control, the two coordinates are here. Orbit control, the coordinates are here and here. That's it. Requirement. As I said, it can be 10 years, 8 years. It doesn't matter. Yeah, you must work for 10 years without any rest. That is the attitude control system's job. So amazing, huh? So you must design a very, very robust system. You must design a very, very robust system. Okay? Reliability and no opportunity for maintenance. This is a very, I think in a satellite technology, also we mentioned this before, very, very prone to failure. So what, for active control system, our redundancy policy is important especially. Now, there is two redundancies that you can do. You can do software redundancy, you can do hardware redundancy. You try to do hardware redundancy, better fly two satellites separately. That's what happens, let's say in GPS, for example. GPS has a lot of satellites, right? Clusters of satellites. They have also backup satellites together. Because if you want to do a backup in highway, in a, what is that, backup of, what is that, equipment, then you might as well just have another system, the hardware. Can you imagine, let's say you have 5 subsystems, and you want to have a hardware redundancy on the 5 system. It's practically another satellite, you know. Let's say a satellite have 5 systems, and then you say, I want to redundant, I want to make sure every have a backup. That means my battery fails, I have one backup. So you will have another satellite in here. Might as well just separate this. So you don't do hardware redundancy, you only will do software redundancy. But in a very, very critical system, you may compromise yourself to do 1 out of the 5, you may have 1 redundant. Yes, that's possible. We will see that. In an active control system, there is some redundancy policy that we do major in software, but there are hardware redundancy that we do, but very, very minimal. We have to do. Now, please understand this also. When active control system fails, mission is gone. Done. You are as good as, so which means that maybe hardware policy is important. So chances of a battery failing is lower. Even a battery fail, maybe you can actually reduce the mission, but mission can still fly. But if your ACS or active control system fails, you are done. You are going to do this. What you can do with this? It's just another debris flying over planet Earth. You can see and just say bye-bye. That's it. Nothing else. Definition, quick ones. Control loop systems. Okay. Process. This is again, you would have seen this in control system. There is a process. Plan. And the plan will come with the models, disturbance models, something disturbing the plan. In our case, the plan is a satellite, disturbance is the environment, we need to quantify it. So this is there is a job for you to do this. There's a job. Second job, measurement. You must have sensors to measure. How to measure? Well, it's another job for us to do this method. Actuation. Okay, I need to correct. What can I use? I have this option. How to actuate? How to control these actuators? Another job for us this semester. Control algorithm. Must put everything together so that they are working together. How can we do this? Yes, we can. We have done control system. So here, almost you are there, but you are not yet there. But this, and then you can bring it together. This you have done. Assume that part that you have done control system is very, very similar to here. This is what you have done. This is very, very familiar. Algorithm or controller, actuator, hardware. Disturbance, you cannot see sometimes, so it is not hardware. If you go and open the satellite, you only will see this, and this. You won't see this. Please understand. You go and open the satellite. You can where is the controller? You can find here. Where is the actuator? Yes, there. Where is the sensor? There. Where is the process? Where is the plant? The plant is, well, this is the plant. But where is the plant? The plant is a model. and you don't also see this. But you can see this. The output you won't see, but you can feel it, you can measure it. But this is actually what happens to the actual controller, the process, or rather the plant. Okay. Orbit motion. Orbital motion, circular, these are the typical orbits that we have learned. This is again, I want to just clearly define. We are very close, but we are different. Very, very close. People sometimes get very confused with orbit and attitude control because it's very close, but yet it is different. Okay? So again, this is basically our orbit corrections are always impulse shaped. That means what? Impulse means you have learned this in satellite technology, propulsion system. On, zoom. Let's say 0.1 Newton. 1 second. So it's impulse. Okay, it gives you impulse just like that. And close. It's open, close. Propulsion system, open, close. That's it. Attitude, open, you don't close until the mission dies. So that's the difference. Let's do that. It's also 2D basically for each and every axis. How we want to evaluate the axis? What I say is 2D is this. No, the whole system is 3D. Don't get confused. The whole system is a 3-dimensional system. What I say for each and every axis, we evaluate it as if as a 2D. Because remember this, I told you. This moves, you only see this moving. This is what I'm saying. Same goes for the other two. If this moves, you only see this 2D move. You don't see this feature. This is what I'm saying. That's how we build the equations like that. But it is a 3 degrees of what is that? Degree of freedom system. Okay? 3 degrees of freedom system. Now, when you say that disturbance, there's a disturbance outside. So it is actually a BIBO system. Maybe you have heard of BIBO. BIBO system, bounded input and bounded output. Your input is bounded by the actual disturbance. Your output as well. Okay? So both are basically bounded. So we need to write the boundary conditions clearly. External torques also. External torques, you see, look at that. We need to also know. For example, there are aerodynamic. You understood this in space mechanics. There are aerodynamic perturbations. There are gravity perturbations. There are magnetic perturbations. There are solar pressure perturbations also. All of them are going to disturb our Keplerian element, 6 Keplerian elements. Okay? But how we are going to actually do that? And look at the nature of that. It is actually with respect to the orbital frequency. That means as long as you are alive, they keep on disturbing you, You cannot run away. Every second they are disturbing you. This is the worst compared to even in orbital mechanics. In orbital mechanics, you can remember them only once in a year. But here, every second you cannot forget them. Because they are function of orbital frequency. And they are constant, and their natures also, they have constant ones hitting you. They are harmonic ones. The constant one is terrible because constant one keep on actually pushing you up. The harmonic one will push you up and pull you down, push you up and pull you down. So you are not going anywhere actually. Yeah, you're going up and going down. It's okay. You are not going up just like that. Okay. So the process that we want to do. This is I'm back to my definition of my whole control loop that you have defined. You have learned that in control system. I am redefining for my purpose here, which is the process. What process it is? Attitude kinematics must be there, which means is this. In order for me to know how this can react with this, I need to establish a relation. Yes, I need to know how. How can I give this to here? I need to have a model here. I need to understand how this will react. I need to model this. So in order for me to do that, I need active kinematics. I need to establish that kinematics. I need to establish with respect to this is ideal, right? This is what you want. If let's say your body coordinate remains as local vertical, local horizontal, do you have any problem? You won't have any problem. But the fact remains that they are not like that. Every time they are not. They are always having this. Look. They have an angle here. Always they have it. Why? Because somebody is displaying. Look, somebody is pushing this. Who is doing this? All the disturbance, aerodynamic, you have all these guys are doing. They are disturbing. So when it's disturbing, it becomes like that. So when it becomes like that, when you draw, yes, you have this. Ideally, the 2 must be on Y. The 3 must be on the Z. The 1 must be on your X. No problem. No problem. You don't need anything. Okay. Then look at this big group now. Attitude determination. My God, so many things that we can look at. We can look at planet Earth. Okay, I'm telling you. For example, when I'm going to fly to planet Earth, I know planet Earth is there. I look at planet Earth, then I know planet Earth is there, right? Remember, I told you always open your eyes when you do attitude control. Eyes must be open. So when you see that, okay. But when you turn the other way around, can you see the sun? Can you see the planet Earth? You can't, but you will see the sun. Sun is here. Planet Earth is there. I can see the planet Earth, I can see the sun. So which means that I can use the Earth and sun as my guidance. Okay, no, okay, very good. This can be my source. Geomagnetic field. Geomagnetic field has intensity, right? Very near to planet Earth is very strong. Further to planet Earth is very weak. We can use that. Let's use that. Gyroscope. Aircraft is gyroscope. Why can't we use it? Spacecraft. We use that also. So at least we know. We know we can. There is two bodies, two things actually we need to be. We will tell exactly after what exactly that we need to have. Please do look at all the measurements. And this is extremely important. All these are very important. Look at the measurement. Now, what you want to establish, what you need? You need the attitude, which is the angle. When you have a roll your pitch, you will have to have the roll your pitch angle. And another one, you need to have the rate. These are the two quantities that you need to have to do attitude control. Remember. So this measurement should take care of that. It should give me the information. Then I can actually hack on my control system. Force generation. Please put this into perspective, please. Force generation can be only done by thrusters, propulsion system. But this propulsion system is quite unique. If you correctly put it, it can give you translation motion. If you put it otherwise, it can give you the rotational motion. You put a thruster here, it can give you translation motion. You put a thruster here and you put a thruster downward, it can give you a rotational motion. Can be used for attitude and can be used for orbital control. But more important, where you are going to put your divergence. That means your thrusters. That is important. Then you have a torque generation. So for torque generation, how to generate the torque? So this one here, force generation, force and torque generation can be by thrusters. Here there is only torque generation, only torque. Thrusters, only torque. Both can manipulate he calls momentum wheel. We will see how they look like later. Yeah? Now, torque is rotational. Okay? So therefore, active you want rotational. So related to rotational. Control. There are activities that you are going to do. Rate damping. Why rate? When you need we will do an exercise when you understand that when you want more torque, that the change of speed, let's say you are cycling, constant speed. But if you want to increase the speed, you need to cycle faster. That means what? You have to give more torque. How to generate this torque? This torque can be generated if your speed increase from one to another. So there is a change of angular velocity. And change of angular velocity will give change of torque. So rate damping is needed. Why? Because when you want torque, when you want this attitude always changing, you need something, this is some torque keep on changing. Now, in order for us to keep on changing the torque, we need to keep on increasing the speed, right? The velocity. That means you have to keep on cycling too high, up to maximum. Then you can't cycle anymore. Then what you want to do? You need to slow down. Huh? That's called rate damping. Then if you need more torque, then you start cycling again. Please understand, that's how the explanation goes. Then you have a rotational around predefined axis. This is basically to get that. This is you can do slew maneuvers. This one. I want you to point here, planet Earth. I want you to point 45 degrees from here. This action can be also done when you give enough of torque. Torque is going to turn you. Rotation. Momentum management. When you have a rate damping, rate damping means what? That means you have more and more torque. When you have more and more torque, obviously you should have a change of momentum. Okay? Momentum H or L is J omega. Inertia times by what? Angular velocity. Okay, J omega. So change of angular momentum is torque. That is basic. All of us know that. So when this keep on increasing, you need to manage the momentum. That's what it says. You need to manage. So that's why you keep on cycling maximum. Can you keep on cycling maximum for the rest of your life? You can't. They are operating 5 years or 10 years. So they already cycle to give you torque. Already maximum. Are you going to leave them to the maximum speed for the rest of their life? No, they will die. Bring them back to the normal speed again. When you need, you ask them, they will cycle for you. That's how the whole system works. Constant pointing. Goal is always deviation is 0. Means this. If 0, what happens? Everybody is together. But it will never happen. Cycling. Good things is very difficult to happen. Bad things always happens. Right? Okay. So, yep. Alright, there you go. Now you have control laws. You have non-linear and linear. You have, I think, learned linear control law. I just want to know that. I just want to let you know that non-linear control law typically comes from a famous device like clusters, because misfiring cannot exactly give me that amount. It's not easy. So you will have the non-linearity then. Okay, but like other momentum wheels, etc., you will get a good linearity. We will see later. Okay, now I will repeat this. Today is the first day you will be exposed to all this device. Now, you need to master all this device towards the end of this semester. So when maybe at the 13th week or 12th week, I will ask you, maybe gravity gradient. What is the principle? And what device is that? And what is the limitation? When to use this? Okay, look, I divided nicely for you sensors and actuators. Sensors, you know from which the plant, you know, right? Where to put? Here. Actuators here. Okay, let's go back. There you go. Sensors. Remember I told you, magnetic field can be sensor also. Optics can be sensor. Why? You have sun, you have earth, you have star. I forgot. Actually, you have star. Yeah. Then you have a gyro. Yeah, you'll be using in aircraft. Why not use it in spacecraft also? And this is the limitations. Orbit knowledge, yes, available. Eclipse, you can't. Sun, eclipse, gone. Earth, no bad. Only for low Earth orbit. But if you are in a very high Earth orbit, let's say geostationary orbit, Earth sensor might be ineffective. Okay. Star sensor is no problem, but very expensive. Very, very expensive compared to other sensors. Huh? No issue. But don't forget, limited of a field of view, obviously, but it is very accurate compared to others. Gyro, no attitude information. No, it means that what? You need an initial attitude information. That is always a problem with gyro. Okay? So that calibration, the initial initiation attitude is what once you give, you actually start refining. Yeah? So there is algorithm to do this. Okay. Measurement actuator, again we can use measure, we can measure with geomagnetic field, magnetometers we can measure. I think you have seen in the lab magnetometers, magnetic field we can use as an actuator, magnetic coil. Magnetic coil will become a magnet force. The other one just sense what is the intensity of the magnetic field. That's all the difference. Then a reaction wheel, it is just a wheel which rotates. You cycle, remember the story of cycle. You cycle fast, you give torque. So imagine you have 3 axes, you cycle here, cycle here, cycle here. Keep on cycling, you want more torque, keep on cycling, you give. You give up torque here, give up torque here, give up torque here. But you reach maximum, you can't on more. You need to actually slow down. Otherwise you end up dying. Okay, so need to do that, clearly. Then you have a propulsion system also. You can do 2. Gravity gradient, this we will, I'll give you an example. When you see Newton's law, I've also taught us how basically this gravity is going to act. The more you go, the less pull. So let's say you're nearer, this pull is stronger. So when this pull is stronger, there is this motion it can have, right? So if I can cleverly do this motion, it can turn into also a torque. This one. Because you pull here more, because you are nearer to planet Earth, this tilts up. So that is right. Then you have aerodynamic. You can also do aerodynamic as an actuator. I think we are exploring this now in the department. How to basically do use aerodynamic torques basically to do actuation. And solar panels. Solar panels, this is solar pressure, it's different. We can even use the solar panels basically to get torque basically, yeah. But more important, okay, you see that solar pressure, because sun has a solar ray, and you have a proton hits the surface basically, proton has mass, and then hits the surface, and surface can be tilted. If you keep on heating, surface can be tilted. So cleverly you put the surface along the sun, then you can get that torque. But unfortunately in eclipse you can't use this. typical satellite. All those items which I've mentioned practically. You have gyro. This is the initial reference unit, initial reference system. You have gyros. You have reaction clusters, sun sensors. You have momentum wheels, sun sensors. All those. These are just to tell you how you are going to actually bring all these system basically into play. Yeah? Alright, if you want to put all of them together, this is what you're going to have. The model. This is all goes into your active control, active operating system. Okay. All this is what you can't see this. This is what happens. Okay, explain. You have a attitude control law, which is the plan, and you have the actuator. Just now, actuator gives the actuation to the satellite. Satellite moves. Somebody detects. Who detects? Sensor detects. Sensor tell you, hey, you move 1 degree. Again goes to the control law. Control system again tells him, hey, move back another degree. This goes on and on and on. Orbit is the same. Keplerian element, X, Y, Z. Measure, sensor. You have a orbit determination done, and you can inject here. Remember, here I've given this dotted line. Huh? You can inject here and calculate, and then accordingly command orbit control system to release. Because assume you are using the clusters here also, then the command can be coupled here. Okay, so this is just telling you this is not independent. This is supposed to be orbit determination, goes here, come back here, sensor. But this can be coupled because I have my control law also for my thrusters here. Thruster can do orbit control. So you can calculate together and then fit back here. How much you want to control the orbit. Remember, the daily job is here. Daily job is here. This one, maybe 2 times or 3 times a year, if necessary. Okay? Typical task or mode, attitude acquisition. You want to actually do attitude. This is when typically what you want to do is that when you want to, after the launcher launches the satellite, first you want to do attitude acquisition. So you do earth pointing, sun pointing. You want to know where you are. Earth is here, sun is at the back. So this is what you do. First thing, so you know where you are. Second, save altitude. This is basically you want to save power. For example, there's some problem in your aircraft, a spacecraft. What do? You go into this mode saying that I'm just going to actually make sure I have enough of power. Remember, power is the most important thing to operate. Enough of power, my thermal conditions are all good. Mission, abort. No mission. Safe mode, no mission. Safe mode means just survive first. Just survive first. Okay. Nominal, fantastic. So 3 typical phases are there. After launcher takes you to the point, inject, attitude acquisition. This is actually when you have a problem, then you go in safe mode. Mission would not be on here. Mission would not be on here. Attitude acquisition, no mission. No mission. Nominal, yes, mission. What is your mission? Earth observation, nominal mode. This is something very interesting. For those who have already learned rocket technology, please look into this. This is exactly where Earth will, active control system comes in. You already look at the sequence. Already you start the acquisition, basically. You start the process. Okay? 1 to 13. This is very, very familiar because we have done the launcher, remember? So this is just the process. Please go through this quickly. Then you know where given injection dates, injection times, up to the nominal mode. we will work on this contribution sequence. Last is a glossary. All the glossaries that throughout if I use. So please take this as a reference. Okay, with that we will slowly start going deeply or deep diving into the subject matter soon. Thank you.